So from this lecture, we are going to start a new module where we will spend a few classes. And this module again will be related with the amplifiers. So we will continue to study amplifiers, but this time we will see that how the gain of the amplifier changes with the frequency. So although our study is going to focus on the amplifiers and we will pick those amplifiers one by one, but this topic, frequency response, is not only confined to amplifiers, but it can be studied for any two-port network. So let us see that more precisely what do we mean by frequency response of amplifier, and then what is the region that this frequency behavior arises, and then finally how do we make a plot of frequency response in a quick and approximate way. So these are the three things that we will study. So first, about the frequency response. So here we have our amplifier, and this is our input port, this is our output port, and what this amplifier will be fed is with input voltage given by, say, Vp sine omega t, and on the output side what we will get is output voltage, which will be AV times Vp sine omega t. So here we see that we have similar sinusoidal output and sinusoidal input. But up till now, we have been focusing on what happens to the amplitude of the amplifier. Now, if you take the case of CS amplifier, for example, this one, then if we give Vi is equal to Vp sine omega t, what we are going to get is Vo minus Gm Rd into Vp sine omega t. Right. So here we see that we have voltage gain AV, which is minus Gm Rd. So in this case, this voltage gain is free from frequency. That is, it is independent of frequency. And if you plot this voltage gain with frequency, let us say the magnitude, then this is going to be a constant of value Gm Rd. Right. So here we have plotted the magnitude, but we see that there is a negative sign here also in the gain. So what is the consequence of this negative sign? That this output is actually like this. Vo is equal to Gm Rd sine omega t plus pi. So do you see that we had given input which was sinusoidal, output is also sinusoidal, but output is now shifted version of the sinusoid by angle 180 degree. So we say that the amplifier not only changes the amplitude of the input signal, it also changes the phase of the input signal. So in general, if you see any amplifier, and if you are giving input Vi is equal to Vp sine omega t, what you will get on the output side is amplitude enlarged, of course, but the phase also shifted by a certain amount, right? And it was this phase for the common source amplifier 180 degree, which manifested as the minus sign here, right? So in general, when you talk about the gain AV, there will be two aspects, the magnitude and second will be phase. So how we define the magnitude of this AV? This magnitude of AV is actually the ratio of the amplitude of the output to the amplitude of the input. Okay. So this mod AV is amplitude of output to the amplitude of input. Now how phase will be defined? Phase of this AV, this will be phase of output minus phase of input, and that is what we see here for this case, common source amplifier. The total phase, keep in mind, for any given sinusoidal signal, the phase part is this argument, because in mathematics we write sine theta. So this is theta, the whole argument of sine or cosine function is the actually the phase of the signal. So this is very important, you should keep in mind. Many students, they are confused about the phase. They will always say this part is the phase, this part is the phase. That is wrong. So when we say phase of the gain, we are, you can see, finding the difference of the output sinusoid to the input sinusoid, right here. So the frequency response of an amplifier is basically these two plots, omega and magnitude of the gain and phase of the gain with respect to omega. So frequency response of an amplifier basically means these two plots. So the first question that here will arise is that what possibly could lead to the change in the frequency response. If you see the common source case, now let us consider common source case, then we find that these two plots are going to be like this. Here we will have GMRD, and here we are going to have, say, 180 degree, right? So here we see that both the plots, they are here, and similarly the phase can also be something like this. That means both the magnitude and phase of the gain of amplifier will vary with frequency. So the question arises, what will be the region for this variation if it occurs? So answer is that the circuit, the equivalent circuit equivalent circuit contains frequency dependent components like capacitors or inductors. So now if you recall all the amplifiers that we have discussed, and if you see their equivalent circuit, you will see that that circuit, however complicated it might be, contained only dependent sources and resistors. So we know that behavior of these two components, they were independent of frequency, and that is why the voltage gain expression that we obtained were independent of frequency. So now if the circuit contains capacitors or inductors, then we know that their corresponding impedances, say for capacitor, this is going to be 1 by j omega c, and for inductor, that is going to be j omega l. So because of this, then the frequency dependency will get introduced in the circuit, and voltage gain that you derive expression that will contain these frequency components. And in that cases, the plot that we just now saw were flat, completely horizontal. They will no longer be horizontal, they will change with frequency. So we see that these capacitors and inductors, they are responsible in real life. So in most of the amplifiers, it is the capacitor which will be responsible for introducing the frequency dependency. And in all of the amplifiers, these capacitors, they occur at two locations. In the circuit, occur at two locations. First is in the circuit itself, that means outside the MOS that are used in the circuit, and second is inside the MOS. Right. So for example, if we take the example of outside MOS case, then we can revisit a common source amplifier right here. So we have been always talking about the amplifiers with infinite load. So here ZL is infinite, open circuited voltage gain. This is what we have been calculating. But when you go to real life, something will be connected here. An impedance will be connected here. And let us take one example that this impedance that is connected here is of capacitive nature, and for simplicity, let us take it is a pure capacitor like this. So this is the example of capacitor or the frequency dependent component appearing outside the MOS. So here this is the MOS, which is the heart of this circuit, and then we have capacitive load. So now here you can see that you can draw the small signal model even with lambda or without lambda, it does not matter. So let us take lambda is equal to 0 case. So in this case, AB, if you calculate, will turn out to be RD parallel with CL. Because here you can see that CL and RD, they are shorted here, and their other end is going to be AC grounded. So CL will simply appear as a parallel element with RD in the small signal model that you will write to find out this voltage gain, right? So now this RD parallel with CL basically means that this RD impedance is in parallel with ZCL basically, where ZCL is 1 by J omega CL, right? So here one can find out the voltage gain AV. This will be equal to minus GM RD divided by 1 plus J omega RD CL. So this is going to be the expression for voltage gain. So here now you can see that voltage gain is now the function of frequency, right? So here this has become function of frequency. So plot in this case is no longer going to be flat parallel to frequency axis. So here one can find out what is the magnitude. So this magnitude is going to be equal to GMRD divided by square root of 1 plus omega RD CL whole square, right? So this is going to be the magnitude, and if you see the plot with respect to frequency, so here we see that when frequency is zero, then its value is going to be GMRD. In fact, this is going to be the maximum value that you can get. And then as the frequency increases, denominator increases and AV will decrease. So this will gradually decrease and it will become zero at omega is equal to infinity. Right. So here you see that for omega is equal to 0, the gain is GMRD. And that is why this is also sometimes called as DC gain. And that is why if you recollect the analysis that we have carried out, many of the authors, they will say that what we are deriving is DC gain. So actually that is not correct. We always talk about gain with certain frequency. It simply says that frequency is very, very small. So, and in that case, that is why this is also sometimes designated as KV naught divided by 1 plus omega square RD square CL square to convey that AV naught is gain at omega is equal to 0. So, and qualitatively also you can appreciate that why gain decreases because as the frequency increases, the impedance offered by this capacitive path decreases. So when the impedance offered by capacitive path decreases, on the whole, this impedance is also going to decrease. And that is why on the whole, this gain is also going to decrease. So qualitatively also, one could have predicted that as the CL increases, AV will decrease. So this is about the magnitude. Now here you can see that this quantity, AV in general, it will have a phase also. And the meaning of phase is that if you feed a sinusoid here, sine omega t, output of course is going to be sine, but there will be certain phase shift that the sine will be not same as this one. Both will not exactly overlap with each other. Of course, there will be amplitude aspect also. So this is the meaning of phase of the gain here. So that phi, which we will see the phase shift in the output sinusoid, will be conveyed by phase of this voltage gain. So now you can see that when you try to find out phase of this will be phase of numerator minus phase of denominator, right? So here we have numerator as minus GMRD. So its phase is going to be pi, because this can be written as GMRD e raised power j pi. Similarly, denominator can also be written as a magnitude denominator e raised power j theta, right? Where theta is going to be the phase of this denominator, which will be tan inverse omega RD CL, and d will be the magnitude of this denominator, right? So here you can see that this phase, this is going to be pi minus tan inverse omega RD CL. So now we can do the phase plot also for the voltage gain. So here we see that when omega is 0, this second term is going to be 0. So the maximum phase that is possible is pi 180 degree. This is the maximum phase possible. And when omega becomes infinite, for omega infinite, this tan inverse infinity is going to be equal to pi by 2. So therefore the phase is going to be pi minus pi by 2 is equal to pi by 2. So the minimum phase that one will obtain is pi by 2, and this will occur at the infinity here. So this curve will start from here and touch this pi by 2 line for infinite omega. So it will be something like this. Right? And when this value is equal to 1, in that case this tan infinite is going to be pi by 2, pi by 4, right? 45 degree. So there is going to be a frequency called omega naught, such that omega naught RD CL is equal to 1. This is a special frequency where what you will have here is phase will be 3 pi by 4. So we say that this is the transition frequency. Before this it will be high, before that phase will be low. And this frequency omega naught is equal to 1 by RD CL will have influence on the magnitude response also, because for that case you can see that this value is going to be equal to 1. So AV is going to be AV naught divided by square root 2. So we will return to these frequency points. We will talk about it later on also, but just keep in mind these critical frequency points, right? So this is the frequency response of a common source amplifier which has a purely capacitive load. So this is the example of outside capacitor in the amplifier. And the second set of capacitors that occur in amplifier circuit are inside the MOS. So up till now we have been taking MOS like this, equivalent to this thing, right? So this is what we have been saying is our MOS. But in general, we will see that there are various capacitors inside. And why those capacitors arise? Because we will see that there, in fact, we have already seen there are electric field originating from one point and terminating at other point. So one can always define capacitance between those two nodes. So there will be capacitances between these drain, source, and gates. And because of that, there will be various capacitors. And as soon as capacitor appears between any two nodes, it will start offering Suppose you have a network like this, and there is a capacitor here. So this capacitor will be equivalent to one impedance given by j omega c. Now, as the capacitor value increases, this impedance is going to decrease. That means the current that will flow through this is going to increase. So this will inevitably change the current flowing through other branches of the network, and it will invariably change the voltages between these two nodes and other nodes also, wherever there are certain other nodes. So as soon as capacitor value becomes sufficiently large, capacitor will start having effect on the network. Not only this, if the frequency also becomes sufficiently large, then this impedance, which is typically infinite for small c and small frequency, will become significant, and it will again start influencing the current in the various branch, including its own branch. So we see that if there is capacitor between any two nodes, its effect will become visible. It cannot be neglected as soon as either C is large or omega is large. So these capacitors occurring inside MOS, they are very small, and that is why their effect is visible only when frequency is very large. However, the capacitors occurring outside MOS, they will be typically large. So even for small frequency, they will have a strong effect on the frequency response. So these capacitors, they are large and these are small. Okay, so this is basic things related with the frequency response. Now, as I pointed out, we need not always talk about the frequency response of amplifier. In fact, if we have a network and the network is linear, right, we are going to use this term S, which for our case will mean j omega, but in more general, S has a different expression than this one, but we will keep taking this equation for the definition of S. So if we have a network and the network is linear, that means the output is going to be constant multiplied by input, and that constant we will designate as Hs. And we will see that this Hs characterizes this two-port network, and this one in general will be called as transfer function. For amplifier, this transfer function becomes gain, say voltage gain or maybe current gain. For amplifier. So this frequency response of any network can be discussed. And so when we discuss the frequency response of network, we basically discuss the plot of this Hs. Right. So frequency response of a network implies again these two plots, the magnitude plot of transfer function with respect to frequency and the phase plot of the network with respect to frequency. Right. So here you can see that the independent parameter is S, which is basically frequency. So in general, this expression is going to be S dependent. Right. So if I know the expression for this, of course I can substitute S is equal to j omega and find out the expression for h j omega, and then from this you do these two plots. So this can always be done, but in many cases, even if you have this expression, uh, this plot cannot be so easily plotted manually. You will have to take the help of a computer because the expression for this transfer function might be quite complicated. So it is now important that we find out some quick way of doing these two plots. And plot should be sufficiently accurate. It need not be 100% accurate, so that we can take its help to fulfill our desired design specification. Right. For example, for the common source amplifier example that we discussed just now, if you have the approximate plot for the voltage gain, you can try to see that how much gain you will get at certain frequency. If it fulfills your requirement, then fine. Otherwise, you will try to do the modification. So we will see a technique using which we can find out approximate uh, frequency response if we know the transfer function. So that technique was developed by an engineer called Henry Bode in 1930s. So what we are going to now study is called Bode plot of, let us say, HS, and this Bode plot is basically plot of magnitude of the transfer function and the phase with respect to frequency. And this Bode plot is approximate and actually this is so asymptotic plot. As we know, asymptote are the tangent to any given curve at extreme values of the variable, especially at infinity. So we'll see that this Bode plot that we will do, they are going to be actually consisting of tangents to the actual uh, plot that one would have got. So that is why they are called asymptotic plot, and because they are asymptotic, so their uh, these plots, they are going to be accurate only at the extreme values of these omega, and typically two extreme values are 0 and a very large value infinity. But it nevertheless it gives a very good idea that how the behavior of the circuit is going to change with frequency. So we will see that how this Bode plot are created for any given transfer function Hs. So we will first see how this Bode plot is developed. So here we have already seen this is always going to be ratio of two polynomials. So this and this, they are both are going to be polynomial in S. That means in j omega also. Right. So now we will take a very simple example and try to see that what is the Bode plot for that. So suppose this is itself equal to simply S. So here the frequency response will be given by j omega, and we want to plot the magnitude and phase, and this we do in log domain. That means both this x-axis and y-axis, they are log. Here this will of course be degree. So we will see that why we go to log domain. But let us see for this case that what will be the plot. And in this case, for simple cases, the Bode plot actually is going to be exact also. So if the transfer function is very simple like this one, this example that we are considering, in that case, the Bode plot will be exactly equal to the actual transfer function plot. So here we go to log domain, and the transfer function in log domain, or which is also called decibel, is defined as 20 log mod of h j omega here. So if you take 20 log of this equation, both sides, then here we continue to designate h j omega, and we will say that it is in dB scale, and this we will say 20 log omega. So what we do here is, on x-axis we plot log omega, and on y-axis we take log magnitude of h, and this will be in dB. So this is the convention, and it has great advantage in simplifying or finding out these plots for more complicated transfer functions. So we'll see the advantage of going for this log scale. So here you can see that what we have here, y, so this is equivalent to y, and this is equivalent to x. So from this convention, we see that this equation that we have obtained, equation number 1, it gets reduced to y is equal to 20x. So this plot on this log axis is going to be a straight line with slope 20, and it will pass through origin. But now the origin is log omega, implies that omega is equal to 1. So on this log axis, 0 does not mean omega is equal to 0, rather it means omega is equal to 1. So we can see this log axis in more detail. So suppose we plot all the frequencies. So this is 1, 1, 2, 3, 4. So this is 10. So if you take if these are the actual frequencies, so these will be log omega. So on the upper side, I have shown all the log omega, and the lower side, I have shown the actual frequencies. So here will be 1, here will be 0.1, this will be minus 10 raised to minus 2. So this is minus 2, minus 1, and this is 0. So what we will be showing here in all of these is values. So they will be actually log omega, but we will be showing them in this convention so that it will be easier for us to read what are these frequencies values, right? So if you specify frequencies values like this, you will have to take the anti-log to find out the actual frequency. So that is why in the this log plot, we will show the frequencies from this convention. Okay. So here we have seen that the slope is equal to 20. Now let us see this thing in slightly more detail and see that how we actually specify this slope. So here suppose we take two x values, say x1 and x2, and corresponding we have y1 and y2. So we have basically taken two frequencies, omega 1 and omega 2, and correspondingly we will have h1 and h2, right? So here we will have y2 is equal to 20 x2, y1 is equal to 20 x1. Now if you find out the difference, y2 minus y1, this will be 20 minus x2 minus x1. Now when you go to log domain, this will become 20 log h2 minus 20 log h1 is equal to 20 log omega 2 minus log omega 1. So this becomes 20 log h2 by h1 is equal to 20 log omega 2 by omega 1 here. So now if you take omega 2 is equal to 10 times of omega 1, whatever may be omega, omega 2 is 10 times. So this case will imply 20 log h2 by h1 is equal to 20 log 10, and this will be 20. Right. So here we see that, so how we specify this slope. So we say that h increases by 20 dB. So this is the 20 dB increment in h2 with respect to h1 if frequency increases 10 times. If the frequency increases tenfold, then the magnitude of the transfer function or the gain increases by 20 dB, right? So that is why this type of slope, they are also specified by saying that slope is equal to 20 dB per decade. So we say that it increases by 20 dB if the frequency increases by 10 times. Right? And this is a typical convention or the terminology which will be used to specify the slope of various lines when we plot magnitude of the transfer function with respect to omega, both in log axis. 20 dB per decade. To be more precise, this is plus 20 dB per decade. Right. So this is about a simple transfer function. Actually, in this case, the frequency response is also going to be exactly like this, a straight line passing through omega is equal to 1. Now let us take a more general case and then try to see that how do we make the frequency plot. So let us take a more general transfer function like this. So yeah. So as I mentioned that both numerator and denominator, they will be polynomial in S. And this is a transfer function for which we have to do this plot. H magnitude 20 log with respect to omega in frequency, and similarly the phase with respect to frequency again in log axis. So keep in mind these are x axes, they are always going to be log. So one can of course take the help of computer, do the plot of this one, substitute S is equal to j omega in this equation 2 and make these two plots. So that is always possible, but we want to see whether quickly we can get a very approximate, quite accurate plot of this transfer function without the help of computer. So fortunately it is possible, and there are few steps that we will have to take. So I will specify those steps. So first step is factorize both numerator and denominator so that we have only first order terms. So here you can see that numerator is already in first order. This is first order, this is a constant, so this is 0th order, but denominator is of second order, s square. So here the factorization is very trivial, and one can factorize it easily. So this will become k s minus z divided by s into s minus p. So this is how we will have to do all the terms. They should be of first order like this or a constant. In the second step, so this is going to involve some effort, little bit effort for some of the cases, not very difficult step for the cases that we will consider, although it could be very complicated. Second step is going to be easy, what is called HS is written in standard form. Before we go for this standard form, I would like to point out that why we are using symbol Z here and why we are using P here. So this Z is used for 0, and here you can see that when S is equal to Z, H S is going to be 0. So in the numerator, all these constants, they will be designated as by using Z, because they are the points where this transfer function actually becomes 0. So that is why they are called 0. And this P stands for pole here. Why this pole? Because these are the values at which the transfer function will blow out. It will tend towards infinity. So this is the meaning behind these two symbols. Now, what do we mean by standard form? In the standard form, we always try to make this constant as 1. So that can be done easily by taking this Z and P common. So in the standard form, what we do, we try to make these terms always as 1. So now this S will get modified. It will get divided by Z or by P. You can take these two things common. And so here we will have K Z divided by P. So this is the standard form, and in this case now you can see that we have the new constant K dash, where K dash is equal to K Z by P. So this is the standard form. So this is also not very difficult. Third step is even easier. We substitute S by J omega. This is the third step. Now we will see that how the transfer function of or the plot of this transfer function can be made in log axis. So why we moved from here the actual value to log axis? So we are going to work out the step 4 in a lot more detail. This will reveal the advantage of log axis. So now here we move to log axis. So we take 20 log on both sides. Here. So left side is simply y. So this whole thing is y. This will go on y-axis and this will be in dv. Right hand side is complicated thing, which fortunately in the log domain gets splitted into simpler terms. So we can do the expansion and this will become 20 log k dash plus 20 log magnitude of 0 term minus 20 log of the pole terms in the denominator. So do you see that now the advantage of log has been revealed? And what is advantage? That instead of plotting this big complicated expression, what one can do, one can plot 4 simpler curves and add them, or maybe subtract them. Subtraction and addition both are similar nature here. So this is the advantage of log axis. Now we will see in the next class that how to get the individual plots for these 4 terms, this term, this term, this term, and this term, right? So if we know the plot for say constant term and for a generalized zero term and generalized pole term, and this is also especially a pole term, but at origin, right? Here you can see that when you take omega is equal to 0 or s is equal to 0, this term will blow out here. But here for this case, omega has to be equal to p. Rather, j omega should be equal to p. So this is called a pole at certain finite value, and this is pole at origin. So if we know the plot of each of these four simpler cases, factors, then we can simply add them to find out the overall plot. So this will give you the magnitude plot. So this is the first part of the Bode plot or the frequency response. Second part is the phase. And for phase also, you can see that that will be easier. When you try to find out the phase of this, we know that phase will become phase of each of these terms added. Numerator terms, they will get added, and denominator terms, they will get subtracted. So phase is simply going to be phase of k dash plus phase of j omega by z minus 1 minus phase of the denominator terms. Here. So this is the going to be the phase plot of the frequency plot.